welcome to my YouTube channel. So here today we are going to be looking at a full paper for chemistry. So this paper is very good for anyone who is doing NS. So we are going to be looking at all these questions. All these will be looked at until gases. So the first question says define the following terms. So defining the following terms, we have the first one, which is the hypothesis. So the hypothesis is also known as an educated guess. So an hypothesis by definition is a tentative, which means unsure explanation to an observation. So the key terms are the hypothesis is a tentative, which simply means unsure explanation to an observation. So when we're looking at hypothesis, it is also termed as an educated guess most of the times. So let's move on to our next definition. Let's look at chemical property. Chemical property. So a chemical property is a property that is observed when a chemical change is observed. So we are looking at this definition. It is a property that is observed if a chemical change is observed. So now what this simply means is that if you are looking at the chemical property, the example that we can give is if you burn paper to produce ash. This is a chemical change in the aspect that from paper you are able to get a new product. So this is a chemical change because a change is observed in terms of the composition. Let's look at the definition of weight. So weight is the force exerted on an object. Weight is the force of gravity exerted on an object. So that's the definition. So weight is the force of gravity. So it is the force of gravity exerted on an object. Let's look at our next one. So we have precision. So the definition of precision, we are just going to say precision is the agreement or consistency of several results in an experiment. So like for example, so we are looking at precision. It is the agreement, that's number one. It is also the closeness, that's number two. And number three, the consistency of several results in an experiment. Like for example, if you get results such as 20, you get 19.9, you get 19.89, then we term this as the results are precise in the aspect that there is the agreement of several results in an experiment like that. So that is what we simply mean by precision. So just an emphasis, some results might be precise but not accurate, because accuracy has to do with how close the measurement is to the true value. Now precision, let's say if the true value is 30, then you are getting 19.9. These results are precise but they are not accurate. So it just has to do with the consistency or agreement of several results in an experiment. Looking at this other one, lists two categories of properties of matter. So immediately they are talking about categories. For this one specifically, the categories of matter. The categories of matter we are looking at, don't say physical and chemical. Because of the word categories, we are looking at what we call intensive and extensive properties. Intensive and extensive properties. We are just required to list down. So just in case the definition comes, intensive, you can just think of it as internal. So intensive is not affected by the amount of substance. Like for example, the density of water, if you have water in a bottle, the density of water in that bottle will just be 1 gram per cubic centimeters. the density of water in the ocean, in the entire ocean, it will still be 1 gram per cubic centimeter. Likewise, another intensive property that we might have is the temperature. So the temperature is not additive. This is done in an experiment. If you have beaker 1, beaker 2, if let's say if here it is 20 degrees Kelvins, this water is 20 degrees Kelvins. When you add this water and this water, it's more like the volume increases, but however the amount of temperature, it will not be like it will be 40 Kelvins, no, but it is not additive, in other words. So therefore it is an intensive property. It does not depend on the amount of substance that you have. Extensive property depends on the amount of substance that you have. The example that we can have is we can look at things such as the volume. The more amount of water you have, the more volume you have. If you have this water, that's the amount of water. Mass is also an extensive property due to the fact that mass would be dependent on the amount of substance that you have. So those are the definitions in case it came. So let's look at the next one. It says that a 2.75 kg sample of a substance occupies a volume of 250 cubic centimeters. Finds the density in grams per cubic centimeter. So we are looking at, that's the mass. So the mass, we have 2.75 kg. Then we have the volume, which is 250 cubic centimeters, like that. So if that is what we have, we are going to say density is equal to mass over our volume. So our mass is equal to 2.75 kg. Remember, the mass is equal to this value. So we are going to say to convert the mass to, they want us to have the units as grams per cubic centimeters. So let's convert this to grams. So it will be times, using the chain link conversion, you are going to put, since the kg is up there, you are going to put it down here. Then on top you are going to put the gram. Now in 1 kg there is exactly 1000 grams. Then in so we have 1 kg there. So this and this ends up cancelling. Then we are going to multiply. 2750 will be the answer if we multiply this and this. So it will be this value, like that. So this will be when you press on your calculator. So with that done, we are going to say density is equal to mass over the volume. So density is equal to the mass is 2, like that, over the volume. Our volume is equivalent to 250 cubic centimeters. So the density should be equal to this value divided by 250 will give us 11 grams per cubic centimeters. We obtain our 2 marks like that. Let's move on to our next question. So for this question, it says 6.35 times 10 to the power negative 4 liters, like that. So to convert this one using the appropriate prefixes without exponents. So what we are going to do is that we are going to look at what is the closest prefix that we know. So if we have power 4, the closest prefix that we have is a -3. So we also have a prefix for -6, but -3 is closer. So we are going to move the decimal point. Now since it is a negative, for you to move to -3 is greater than -4. That means to say you need to multiply a 10. So what you are going to do is you are going to move the decimal point this side, and immediately you do that, it will be a 0.635. Then it will be times 10. Now immediately if you are going to your left, it will be again, so it will be +1. Then you have times 10 to the power -4 liters, like that. So you have your 0.635, then you have according to indices, take one base, add the power, so it will be 1. Now this one is negative, so it will just be minus 4 liters, like that. So you have your 0.635 times 10 to the power negative 3 liters. So it will be 0.6335. Then 10 to the power negative 3 is a milli, which we can write small letter m, liters, like that. So that is the prefix. So 10 to the power negative 3 is a milli, like that. So with that said, we are going to look at this other one. So if we look at this other one, it will be a 5.2 times 10 to the power negative 9. So 5.2 times 10 to the power negative 9 milliliter, like that. Oh, it's it's meter cubed, meter to the third. So what we are going to have is that, is this what we have? Yeah. So we know to say 10 to the power negative 9. We know that 10 to the power negative 9 is a nano. So nano has got a small letter m, so this will be 5.2. It's direct. Where there is 10 to the power negative 9, we are going to put nano, small n. Then we have the meter to the power 3. So this is what they want you to show. So with that said, let's move on to our next question. So we are on this one, converts negative 84 kelvins to Fahrenheit. So what we are going to have is that we are going to have something like this. So if this is what we have, first we cannot convert direct to Fahrenheit, we have to convert to temperature in degrees. So the temperature in degrees Celsius is equal to the temperature in kelvins. Then we have minus a 273, like that. So we have 273, like that. So each and every time you're moving from degrees to kelvins, you have to subtract. Just think of it as the letters K and C. For you to move from K to C, you have to subtract, because that's how the alphabet is. So with that said, we are going to have something like, it will be, so what you are going to do here is, depending on how strict your lecturer is, you can just attach this. So we have, on top we are going to have 1 degree Celsius over, we are going to have 1 degrees kelvins, like that, so that this Kelvin and this Kelvin can cancel. So what we have is that the temperature in degrees Celsius is equal to negative 84 kelvins minus 273 degrees kelvins. Then we have times 1 degree Celsius over 1 degrees Kelvin. So when we subtract this, we are going to get a negative 84 minus 273. This is giving us a negative 357 degrees kelvins times 1 degree Celsius over 1 degrees Kelvin, depending on how strict your lecturer is. But if it's not strict, you can just subtract. So you are going to have something like a negative 357 degrees Celsius, like that. So this is the temperature in degrees Celsius. Oh, sorry, let me use the accurate one, which is 0.15 kelvins, 15, not just, yeah. So when we do that, we are going to have 0.15 degrees kelvins, like that. So what we are going to have is that after we do this, we are going to get the value. We are going to get this value. Let's write the formula now. From Fahrenheit to degrees, we are going to have temperature in degrees Celsius should be equal to, we are going to have the temperature in degrees Fahrenheit minus 32 degrees Fahrenheit. Then we have times 9 degrees Fahrenheit, 5 degrees. So we have 5 degrees Celsius over 9 degrees Fahrenheit. So how I remember this formula is simply, we have numbers such as a 32, we have numbers such as a 32, and you have the temperature in degrees Celsius. Just look at your alphabet, C and F. So temperature in degrees to temperature in Fahrenheit. So if you are moving, if this is the subject of the formula, so you are moving from here to here, you have to subtract, because F, for you to move from F to C, you have to subtract. So that's why we subtract there. So this is the form that it is very easy for you to remember. Just remember that there's a 5, there's a 9. So if you have the C there, it means to say you are going to have the 5 on top, since C is less than F. So you have 5, you have 9 there, in case the formula is not given. So you are going to now substitute direct. So it's either you just know this formula or you know both for the direct conversion, which will give you the same answer. So we have done all these videos on conversions, which you can watch. So we have a negative 357.15 degrees Fahrenheit, should be it's degrees what? Degrees Celsius. Degrees Celsius. Degrees Celsius should be equal to the temperature in Fahrenheit is unknown, minus the 32 degrees Fahrenheit times we have the 5 degrees Celsius over 9 degrees Fahrenheit, like that. So we are going to have, so this is the same as having these numbers can be put in front. So we have a negative 357.15 degrees Celsius should be equal to, this is the same as having this, our 9 degrees Fahrenheit. Then we have temperature in degrees Fahrenheit minus 32 degrees Fahrenheit, like that. So with that done, we are going to cross multiply now. We have 9 times this value. It is going to have, we are going to have, so we have 9 degrees Fahrenheit times, we have negative 357.15 degrees Celsius. This 5 and this one, it comes here, we have over a 5 degrees Celsius should be equal to temperature in degrees Fahrenheit minus 32 degrees Fahrenheit. So let's divide those. We have this value, negative 357.15 times 9. This is going to give us a value of, if we divide by 5, we are going to get a value of negative 642.87. When this comes this side, it will be plus our 32 degrees Fahrenheit should be equal to, we are going to have the temperature in degrees Fahrenheit, which will give us a negative 642.87 minus our 32. This is going to give us, or plus our 32. Plus our 32, this is going to give us a negative 610.87 degrees Fahrenheit, like that. So remember, this and this will cancel each other to remain like that. So this is how we convert that. Let's move on to our next question. So if you're good with the direct method, alternatively, this is the other, when TF is made the subject of a formula, which you can just replace. So this will give us a 9 degrees Fahrenheit over the 5 degrees Celsius. Then we have times the temperature in degrees Celsius, we found it to be 357.15 degrees Celsius. Then we have plus a 32 degrees Fahrenheit should be equal to temperature in degrees Fahrenheit. Remember, even this you can use. So if you are moving from C, that is, if you are moving from C to F, you must add a value. So you add a 32. So just as the alphabet, we have CF. For you to move from C going to F, you have to add. So you can use that if you want to memorize this formula. Then by replacing, this will even be faster. We have a 9 divided by 5. Then we get that times 357.15. Remember, it's negative. This value is negative. So we are going to have negative 642.87. Then we have plus our 32. So we have Fahrenheit. degrees Fahrenheit should be equal to the temperature, like that. So this we have our, when you get that value, you are still going to get the same value of 610.87 degrees Fahrenheit should be equal to the temperature in degrees Fahrenheit. Yeah, so that's the temperature in Fahrenheit, like that. Let's move on. So if you have this, for F, use the exponential notation to express the number 3.85500 to one significant figure. So how do you express this value to one significant figure? So one thing is not, so you have all these zeros. First, you're going to count the number of zeros. So you show this in your work: 1, 2, 3, 4, 5. So you're going to have 3.85500. So immediately you are moving this side, so you add a number. So you have 10. You move to 1, 2, 3, 4, 5 times 10 to the power 5, like that. So that's the first step. So now one significant figure, this number is not in one significant figure. One significant figure means we should just have one number. So if this is 8, it will now be adding 1 to there. So it will be a 4 times our 10 to the power 5. So this is the value that we have. Does it have units? So this is the value that we have. Now, you cannot write 4.0 times 10 to the power 5. This is two significant figures because a 0 at the end is considered to be significant in that sense. So let's move on to our next question. So we have our G, differentiate between the law of conservation of mass and the law of constant proportion. So for this one, we have differentiate between the law of conservation of mass. So the law of conservation of mass talks about mass. This one talks about the mass is conserved. The total mass is conserved. That means to say the amount of mass that you begin with the reactant is the same as the amount of mass that you end up with for the product, while the law of definite proportion states that for any given compound, no matter its source, there is a fixed ratio by mass. So I'll elaborate more. So before we differentiate, let's define. Let's know what this is about. So the law of conservation of mass talks about the fact that matter is neither destroyed or created. Therefore, this means that the total mass of the reactants is equal to the total mass of the reactants is equal to the total mass of the products. Whilst the law of constant proportion states that for any given chemical compound, it contains the same elements combined in the fixed ratios by mass regardless of its source. So before we now look at the answer you are going to represent, let me explain. The law of conservation of mass, let's say if you have your hydrogen reacts with oxygen to produce water, you will find that to balance this equation I'll need a 2 here so that I can have 2 oxygens. We have 2 there. So if I add this, I'm going to get something like 2 times this 2. We are going to have okay, so just for the sake of simplicity, so we know that hydrogen has got 1.01. We multiply 1.01 times this 2, it will give me times 2. We also have this other 2. This will give me a 4 points. So we have 2 times 1.01 times 2. This will give me a value of a 4.04, like that. Plus oxygen has got 16 times 2, it will be 32. So we are going to get a 32, like that. if we add 34 plus 32, we are going to get a 36.04. So same applies with the product. So this is the reactant. Then the products, what we are going to get is oxygen is 16. Then here we have a 2 times hydrogen. There are 2 of them. This is why there is a, okay, these 2 let's account for, okay. So we have a 2. Hydrogen has got 1.01. Then we have another 2 here. So we are going to have plus our 16. When we add 2 times this gave us a 4.04 plus a 16, which is going to give us a 30. So we have 2 times the oxygen, which is 16, is going to give us a 32 there. So there are 2 of them. So we are going to get this. Finally, we have a 36.04. So the mass that you begin with is the mass that you end with. That is the law of conservation of mass. Law of constant proportion or law of definite proportion talks about the ratios are fixed no matter the source. Like for example, if you have water, there will be 2 parts will be hydrogen. The 2 parts will be hydrogen. 1 part will be oxygen. So that ratio is fixed no matter the source. If let's say you have as long as for a pure substance, it will always have the same or fixed proportion by mass. So what this means that is that let's say for example, if you have your water again, let's say you have rainwater, let's say if it is purified and all that, it has to be a pure substance. We are going to have 2 parts. It is still going to have 2 parts of hydrogen, 1 part of oxygen. So that's the law of constant or definite proportion. So the definition or the answer that we can give is the law of conservation of mass focuses on the mass before and after the reaction being constant, whilst the law of constant proportion focuses on the constant composition or ratio in one pure, let's add pure, in one pure compound no matter the source. So that is the difference between the two. Let's go to the next problem. This one says that write the nuclides of the isotopes of carbon. So 3 marks, we expect to write 3 of them. So the nuclide, we are going to have something like this. We have the A and we have the Z. So A, you can add, you can say, you show this, so you have your A will be your mass number, then your Z will be your proton number or the electron number. So we can now show the carbon. We have carbon, so let's use 3 of them. So carbon has got isotopes. So on top for A, we have isotopes such as 12, 13, 14. There is also carbon 11, but unless they give you 4, that's when I would advise you to use that. Then we know to say the number of protons that we are going to have for carbon. So the number of protons is the same. It is 6, a 6, and a 6. So the only difference is the number of neutrons, which does not show on the nuclide notation. So that is the answer for this one. And then when we look at, so you can just write carbon 12, 13, 14, even 11, and this if you're given 4, that is when I would advise you to write that. Name each of the following compounds. So we have our Fe, let me move this. So we have our Fe, Br, 3 like that. So if this is what we have, we are going to get our name. It will be, so the first one, FeBr3, this is made of a metal and a non-metal. So this one falls under what we call type 2 of naming. So type 2 involves the use of numbers such as 2, 3, 4 if there is a metal and a non-metal. So this one will be number 1, it will be ion. Then if the 3 is here, it means to say this was the ion was the one that had the 3 plus, then it contributed to the Br with the positive 1 when they interchange. That's how come it's Fe Br 3 like that. So they interchange the numbers. So this will be ion. You're going to put in brackets, say ion 3, then you're going to say bromide. So this is how we name compounds under type 2. Then if you look at your S2Cl2, this is naming compounds under type 3, which is the covalent compounds, in which 2 nonmetals, so we have sulfur and chlorine. So under nonmetals we use prefixes such as di, tri, we have tetra, we have other things such as deca, nona, and all that. So this one, since there are 2 sulfur, you are going to say di means 2, so we are going to say disulfur, disulfur like that. Then you are going to also put dichloride, so like that. So we have disulfur dichloride like that. The next question requires us to move from lead 4 carbonates to the name. So we have, if we have lead 4, lead has got the symbol Pb, so we are going to have Pb. Pb, we have 4, the valence of 4, sorry, so we can write 4 plus, so that's the symbol for lead. Then carbonate, we have CO3, the charge is 2 negative, so these numbers will interchange themselves to give us something like this. So we have Pb, Pb2, CO3 like that. Then we have this 4 comes here. So if our 4 is here, we can divide the 2 throughout over our 2 over our 2 to make it Pb like that. Then we have CO3, then we get a 2 like that. So this is what they want us to write. So this is the answer for that one. If we look at this one, so we are looking at something like pentaboron. Boron has got the symbol of B. Then penta, which means there are 9 of penta, sorry, means 5. So we are going to write 5. Nona means 9. So hydride, we are going to look at the hydrogen. So we are going to say hydrogen and 9 like that. Last but not the least, we have tetra phosphorus decoxide. So tetra means 4. Then we have the phosphorus, so we are going to write P, that's for phosphorus. Then we are going to write 4 because tetra means 4. Then dec means 10. Oxide, we have the oxygen, then we are going to have 10 of them like that. Let's move on to our next question. So if you have been enjoying the content, kindly like, subscribe, and share for more. You can't afford to miss these contents. So this was the question we were solving. The next question is on stoichiometry. So if we have this, given the data in the table below, we have calculate the atomic mass of the unknown element X, then identify the unknown element which is used medically to treat some mental disorders. So videos have been created where I solve many of these problems. So now, to answer this one, we are just going to say the average, the formula we are going to use, average atomic mass unit will be equal to the percentage of A, or let's not use percentage, let's use the fraction of A times the mass of A plus the fraction of B times the mass of B. So we can just say Fa is the fraction of A. Fb is M is equal to mass like that. Okay, so F, we can just say F is equal to fraction, so that fraction, yeah, so F is equal to fraction. M is equal to mass. So we have mass of A like that. So the fraction can be found by just get your percentage. You know, to say a percentage is a fraction. So just get your percentage. We know that the fraction of A will be equal to the percentage, which is a 7.5%. A percent is always out of 100. So we have 100%. We are going to have the fraction of A will be equal to, we are going to get a 7.5 divided by 100. This is going to give us a 0.075 like that. Then we have the fraction of B should be equal to, we have the 92.5%. We divide this by 100%. This is going to give us the fraction of B should be equal to 0.925 like that. Yeah, so we have, this is the fraction of B. So all we have to do is just substitute. Let's get this so that we can be using it for reference. So each and every time, what are we given? Calculate the atomic mass of the unknown element X. So if you are given these atomic masses, the one that you are finding is the average like that. So this is how we find the average. So we are going to just substitute the values. So the average atomic mass unit should be equal to, the fraction of A in this case is equal to 0.075 times the mass of A. Mass of A is equal to, so the mass of A is this one, 6.015 like that. Then we take it as our atomic mass unit. Then we add it plus the fraction of B. This is the easiest way. Plus the fraction of B, which is we found it to be 0.925 times the mass of B, which is equal to, we have a 7.016. So we get a 7.016 like that. So we can just add atomic mass units. For me, space has run out there. Atomic mass unit like that. So with that done, we are going to have something like this. We have a 0.075 times 6.015. This is going to give us a value of, we have a 0.451125. We add it plus, we have atomic mass unit, plus we have our 0.925 times 7.016. This is going to give us a value of 6.4898. So atomic mass unit, when we add these two, we are going to get plus 0.451125. This is going to give us a value of 6.94095 atomic mass unit. So this is the average. Now if this is the average already, if this is the average atomic mass unit, therefore what we are going to have is that if you look at your periodic table, the mass that corresponds to this is so element X is lithium. Let's move on. So if we have this one, it says that a compound with a known molecular weight, with a known molecular weight as this, that contains only carbon, hydrogen and chlorine, was studied by combustion analysis. When 0.367 grams was combusted, 0.659 grams of carbon dioxide and this were formed. What is the empirical formula and the molecular formula? So to find the value of this, what we are going to say is that we have a compound with the unknown. So there are a lot of them, but we don't know the actual compound. So we have the CX, what else? We can say CX, HY, then Cl, Z to show that these could represent numbers such as 5, 3, or 2, like that. If this is combusted, meaning to say it is burnt in oxygen to produce carbon dioxide and water only, like that. So if these are the only products, now from the law of conservation of mass, or mass can neither be created or destroyed. That means to say if you have carbon in carbon dioxide, it is coming from exactly the amount of carbon that was present in the compound. So now this like that. So if you have let's say if you have the amount of hydrogen, the exact amount of hydrogen that is present, is it hydrogen? The amount of hydrogen that is present here is the same amount that is able to form water there, because it can neither be created or destroyed. It is just more like recombines, like that. So what we are going to do is, let's find the mass present for this and this, then subtract from the total mass. So we are going to say the mass of what? The mass of let's begin with carbon in carbon dioxide. So this carbon dioxide, this carbon is the one that is contributing for the carbon in this carbon dioxide. So we are going to say, it's more like you're just answering the percentage, where you are going to say carbon over the carbon dioxide. That's how we find the percent. If someone has gotten 5 out of 20, we say 5 out of 20. So same here, carbon over the amount of carbon dioxide, then you're going to multiply by the total. So we multiply, if we have 5 over 10 times 100%, 100% is the total. If you want the percentage to be out of 50, we'll multiply by 50%, which will be, this person will get a 25%. That's how they even calculate the CS. So you just multiply by the amount, the total amount that you want. So now in this case, the total amount of carbon that is present, that is the total amount of carbon. Now you are going to say, to say the carbon, the mass of carbon dioxide is 12.01 grams per mole, that is the molar mass. Over the carbon dioxide, you are going to have something like, you have the 2 times 16, then you have the 12.01. So this is going to give us a value of 32, like that. This one, it's a 12.01. So we are going to have 44.01, like that. So we are going to write 44.01 grams per mole times, we are going to have the total amount of carbon that is present there. We are going to have, if the amount of carbon produced was 0.659 grams, so that is what we are going to do. So we have a 12.01 divided by 44.01, we are going to get a, so 12.01 divided by 44.01, then this value we multiply by 0.659, we are going to get a 0.1798, at least 4 significant figures, so that's our answer. So this and this cancels. So this is the amount of carbon present in that amount. So we have calculated the percentage for carbon. It's more like the mass by multiplying by the total mass. So this is very, very simple. So after you do that, you are going now to go to hydrogen. So you are going to say the mass of hydrogen in water, because water is formed. So this hydrogen present in water came directly from the hydrogen there. So you can say amount of hydrogen in water. You can say mass of hydrogen in water. So mass of hydrogen in water, you are going to say the mass of hydrogen over the mass of our compound times the total for your H2O. So we know to say there in water there are 2 hydrogens, so we have to multiply by 2. So we are going to have 2 times, if you look at your periodic table, the molar mass of hydrogen is 1.01 grams per mole, over the molar mass of water is we are going to have 16. We are going to have this 2 times 1.01. So when you add, you are going to have your 16 plus 2 times this, it's going to give you 2.02 like that. So when you add 16 plus 2.02, this will give us 18.02 grams per mole. So we are going to write our 18.02 grams per mole. Then we multiply this by the total amount of water present, which is a 0.0892 grams like that. When we multiply, we are going to have, so we have 2 times 1.01 divided by, come in. So when you divide this, you multiply, you are going to get a 9.999 times 10 to the power negative 3 grams like that. So that is the amount present, that is the amount of hydrogen. So after you do that, then find the remaining. So if you have found the mass of hydrogen, you have found the mass of carbon, then the compounds we wrote was our CX, HY, Cl, Z. So what we are just going to do is that for us to now, we know the mass of this. We know the mass of this. So that means to say the only remaining mass is this. So we are going to say the mass of carbon plus the mass of hydrogen plus the mass of our chlorine should be equal to the total mass, which is true. If you add the masses, it should be equal to the total mass. So the mass of carbon, we found the mass of carbon to be equal to, it was equal to what? 0.1798 grams, plus the mass of hydrogen, we found it to be a 9.999. So we have 9.999 times 10 to the power negative 3 grams, plus the mass of chlorine, which is unknown, should be equal to the total mass. Let's move this a bit. So if we move this a bit, we have the total mass. The total mass for this, according to what we have been given, is when this is 0.367 grams of the sample was combusted, meaning to say the whole thing. So this is our total mass there. So we are going to have our 0.367 grams like that. So if that is what we have, we are going to add, we have our 0.1798 plus 9 plus our 9.999 times our 10 to the power of negative 3. So we are going to get a value of 0.189799 plus the mass of chlorine should be equal to the 0.367 grams. So we are going to take this value the other side. It will be, so the mass of chlorine should be equal to 0.367 grams minus 0.189799 grams like that. So when we subtract, we are going to have 0.367 minus 0.189799, which is going to give us a 0.177201 grams. So this is the mass of chlorine like that. So that is half of the problem has been solved like that. Then all we have to do is that to find the empirical formula, we are going now to say empirical formula. So empirical formula will be equal to, we have the number 1. We are going to write first the mass, then we are going to write the molar mass, then we are going to write the number of moles, then we are going to write the number of moles. From there we are going to write the ratio. So just follow this order: mass, molar mass, mass, molar mass, and that. So let me move the empirical formula a bit. on top here. So what elements do we have? We have carbon, hydrogen, and chlorine, like that. So we are going to write our carbon. The mass of carbon that we found was equivalent to, so if we look at the mass of carbon, we can even just do it from here. So the mass of carbon was 0.1798 grams. The mass of hydrogen was 9.999 times 10 to the power negative 3 grams. Then the mass of chlorine has been found to be 0.177201 grams, like that. Then we are going to have the molar mass. The molar mass is a 12.01, like that. Then we have the molar mass of hydrogen is 1.01, like that. Then we are going to have the molar mass, so we have grams per mole, we have grams per mole. The molar mass of chlorine is a 35.45 using your periodic table, grams per mole. So from here you are going to divide like that. So when you divide, we are going to get a 0.1798 divided by 12.01. This is going to give us a 0. So to find the number of moles, so this is the sign, you just divide them. So we are going to have a 0.01497, like that, at least 4 significant figures, so that your answer is as accurate as possible. Then for this one, 9.999 times 10 to the power negative 3 divided by our 1.01. This is going to give us a value of the same value, which is our 9.9 times 10 to the power of negative 3, like that. Then we have last but not the least, if we divide our, so we are dividing, if we divide our 0.177201 divided by 35.45, this is going to give us a value of a 4.9986, like that. So from here, what we are going to do is that we are going to look at the smallest value among the three. So we have this times, let me move it a bit. Then we have times our 10 to the power space, our 10 times our 10 to the power negative 3. That is what we have. Then for the last part, we are just going to have our ratio. So ratio, you divide the smallest. So if you look at this, the smallest is 10 to the power negative 3, means we have zeros such as 0.00, then we have 99. Then this one, we have 3 zeros, that's the meaning. We have our 10, our 0, this is the same as 0.004498, like that, 9 and something. So we have 3 zeros there. Here we only have 2 zeros, so this is the biggest value. And we know to say 9 is greater than 4, so we are going to divide this value throughout. So if we divide the same value by itself, it is going to give us a 1. It is going to give us a 1 there. So we have a 1 here. So ratio, you divide this value divided by itself, which is a 1. Then this value, you are going to divide by the 4.9986 times 10 to the power negative 3. So just be careful, put things in brackets. So we have our 9.9. Then we have 9.9 times our 10 to the power of negative 3, like that. Then we divide by, we are going to have 4.9986 times our 10 to the power of negative 3, like that. Then we are going to get a value that is equivalent to, we have a 1.98, like that. Then the last value when we divide, so we are just dividing this value throughout. We have our 99 0.86 times 10 to the power negative 3, of which, so when we divide that value, we are getting a 0.01497 divided by, we have a 4.998 times 10 to the power of negative 3. So this value is equivalent to, we are going to get a 2.995. Now we can just round off the ratios. So if we round off, we have a 3 here. Since it's very close, we have a 2 here, we have a 1 like that. So now on the ratio, there is no need for you to show like this, but anyways, you can just show it. You divide it throughout like that, then you have that. Then what we are going to have there is, we have the C attached to the 3, so we have the C3. Then we go to our H attached to a 2, so we have our H2. Then we have our Cl there, so we are going to say Cl attached to a 1 like that. So it will be C3H2Cl like that. So this is how we answer that problem. So this is the empirical formula. Now we were required to find the empirical formula and the molecular formula. So let's find the molecular formula now. So what we have here is this value, the empirical formula. If this is our chemical formula, so we find the empirical formula. To find the molecular formula, we know that by definition, the molecular, you can just write it in full. So the molecular formula is equal to the empirical formula times the N, like that. So find the mass of the empirical formula. Find the mass of the empirical formula, which will be our C3H2Cl like that. We know that the mass of chlorine is 35.45 like that. The mass of hydrogen, we are going to have 2. There are 2 of them, so we have 2 times 1.01 like that. Then we also have our mass of carbon is a 12.03 or 01 times, there are 3 of them. So when we do our math, we are going to something like, we have our 35.45 like that. Here we have our 2 times our 1.01. This is going to give us a 2.02. Then we get, for this other one, we are going to get a 12.01 times 3. This is going to give us a value of, we have a 36.03 like that. So when we add this, we are going to get a, so we have 36.03 plus our 2.02 plus our 35.45. This is going to give us a value of a 73.5 like that. So if it's giving us a 73.5, we are going to say, we know now that the empirical formula, the molecular formula, is equal to the empirical formula times the N value, which N represents a number. So we can put the values. The molecular formula, or the molecular weight, is 146.99. That is equal to the empirical formula mass, which we found to be 73. So grams per mole should be equal to 73.5 grams per mole. Then we multiply this by the N value. Then what we are just going to do is that we are going to divide over our 73.5 over our 73.5 grams per mole, like that. Then what we are going to get is, if we divide our 146.99 divided by this answer, we are going to get a 2 rounded off. We have a 2 should be equal to N. So it has to be a whole number. So therefore, to find the empirical formula, what we are going to say is that the molecular formula, we know that it is equal to the empirical formula times our N value. If the empirical formula is equal to C3H2, then we have our Cl like that. Our N value here is equivalent to we have found it to be equal to 2. So we are going to just multiply there. We are going to have our molecular formula should be equal to C6H4Cl2. So this is the answer that they expected to get the full 10 marks. Let's move on to our next question. So here we have, when iron is produced from its ore, we have the reaction is this. The first question says, how many moles of carbon monoxide are needed to produce that? So the more concept and stoichiometry is one of the easiest things. Now all you need to know is that, let's say if you have a 2 kwacha, the amount of things that you can buy in that money is, let's say, one sweet, like that. That simply means to say, if you have 4, how much will you be able to buy? So automatically you will say 4 times this, it is 4, should be equal to 2 times x, it will be 2x. We divide by 2, our x will be equal to 2. So this is the same way equations behave. So which is true, if you have 2 kwacha, you will buy 1. If you have 4 kwacha, you will buy 2. So now in the chemistry aspect, that's the same meaning that we are going to be able to more like use. Likewise, if let's say you have if you have one paper, let's say these are reactants. If you have one paper, you are able to produce let's say 1 sheet of money or something. That is the more concept. So if we have this question which says that iron 3 oxide reacts with carbon monoxide to produce iron plus our 3 carbon dioxide, 3 moles of carbon dioxide. How many moles of carbon monoxide are needed to produce 35 moles of that? So same approach. First thing you have to make sure is that the equation is balanced. So according to this, the same example that I gave you. So if you have 1, how many moles? So you can have, if you have 1 mole of carbon monoxide, you are required to produce from the equation. That is the same thing. If you have a 2 kwacha, you can buy 1 sweet. So from the equation first, if you have 1 mole of carbon monoxide, you can be able to produce, so you are comparing it with this one depending on what they want. If you are comparing with 3 carbon dioxide, you can compare it with that. There's no problem as long as you're doing what they want. You are going to compare with iron since that's the one you are given, so you are going to say 2 moles of iron, like that. What if you have 35 moles of iron? So you are going to say, what if I have 35 moles of iron, like that? You are going to say you don't know. You are going to cross multiply 2 times x. This 2 times x, it will be 2x. So the more, you can just cancel from here if they are on the same side. So you are going to have, should be equal to this 35 times the 1 mole of carbon monoxide. You divide by 2, you are going to have your x should be equal to, we have our 35 divided by our 2. This is going to give us a 17.5 moles of what? Of carbon monoxide is needed. So let me, is this what we are given? Is the equation balanced? Okay, there's a mistake. The equation is balanced by a 3, very, very important. So we have 3. So this tells you, if we have 3 here, 3, so we are going to multiply our 3 times 35 there, 3 times 35, the 2 is okay, 2 times this is okay, so the equation has to be balanced. So we have our 35 times 3, this gives us a value of 105 divided by 2. This will give us a 52.5. So we are going to say 52.5 moles of CO is needed, like that. Likewise, if how many moles of iron 3 oxide are needed to react with 4.5 moles of if 4.5 moles of carbon dioxide are produced. So the same approach still applies. So from this balanced equation, let's move it a bit. From this balanced equation, we have been told that we have this is the reaction. Now, if the question is saying that how many moles of iron 3 oxide react if 4.5 moles are formed. So using the equation, we are going to say, according to the equation which is balanced, 1 mole of our iron 3 oxide is able to produce, since they want carbon dioxide, that's the one you compare it with, so this should be able to produce 3 moles of carbon dioxide. Then what if, according to what you have been given, what if 4.5 are formed? So you are going to put the 4.5 where carbon dioxide is, so 4.5 moles of CO2. Then this side you don't know, cross multiply 3 times x, so carbon dioxide will cancel, so 3 times x, we are going to have 3x should be equal to 1 times 4.5, it will be so we have a 4.5 times 1 is 4.5. Then you are going to add the mole of Fe2 or 3 like that. Divide by 3, your x should be equal to, we have our 4.5 divided by our 3, which should be equal to a 1.5 moles of Fe2 or 3 like that. So these are the number of moles produced for iron 3 oxide like that. For this other one, it says that how many grams of iron 3 oxide must react to give 0.57 moles of iron. So how many grams of this? So for the sake of this video, we are just going to use mole to mole, then convert. If you are conversant with the mass to mass, you can use it. So we are going to have how many grams of this must react to give 0.57 moles of iron. So we are going to go and write our equation. So this is our equation. We have how many grams of this are needed to react with the carbon monoxide. So how many grams of this must react to give 0.57 moles of iron? So first, let's just find the moles, then convert it to mass, or mass to mass is also okay. So we are going to have our number of moles. According to the equation, 1 will be able to react with 2, so we have 1 mole of our Fe2O3 should be able to react with 2 moles of our Fe2O3 like that. Then that means to say, if we have what if we have this number of moles produced, sorry, not Fe2 but Fe like that. So what if we have the 0.57 moles of our Fe, the amount that will be able to more like react, which is this one, we don't know, so we are going to cross multiply 2 times x, so this one cancels, so 2 times x, it will be 2x should be equal to 1 times this, it will be, the 1 doesn't change anything, so it will be 0.570 moles of Fe2O3 like that. So with that done, we are going to now just divide over our 2 to get x should be equal to 0.57 divided by 2. This is going to give us a value of 0.285 moles like that. So if these are the number of moles that we have, then to find the mass, we know that so these are the number of moles of, which one is this side? It's iron 3 oxide. So to find the mass, we know that number of moles is equal to mass over the molar mass. So to find the mass, we are going to find first, we cross multiply, mass times 1, it will be mass, number of moles times the molar mass. But we don't know the molar mass of iron 3 oxide, but we can find it. So the molar mass of iron 3 oxide, we have a we have our Fe2O3. So we have 3 oxygens. The molar mass of oxygen is 16. Then we have 2 times the molar mass of this, if I'm not mistaken, is 55.85 grams per mole. Now let me just verify on my periodic table. Okay, so that is okay. So we have 3 times 16, that will be 48. Then we have our 2 times 55.85, this will be our 111.7. So 111.7. Then we are going to just add them. So this plus our 48, this is going to give us a value of 159.7 grams per mole, like that. Then with that, we are going to have our 159.7 is that one. Then from that, we are going to now just calculate now. So we have the mass is equal to the number of moles times the molar mass. So the number of moles we found was 0.285 moles. Then we multiply this by the molar mass, which is our 159.7 grams. So the mass, grams per mole, the mass will be equal to 0.285 times our 159.7. This will be equal to, we are going to have a value of 45.5145 grams. So this is our mass for that problem. So from there, let's look at our next problem. So from our next problem, we have how many moles of these are needed to react with 48.5 that. So we can just convert this to the number of moles, then compare. So for the equation that says, so what we have is, we have our 48.5 grams. So let's convert this to the number of moles so that we can just compare direct. If you want, you can compare mass to mass, it's still going to work. But yeah, so we are going to say the number of moles is equal to the mass over the molar mass. So for iron 3 oxide, the mass we have been given is 48.5 grams. Then we divide this divided by the molar mass, which is equivalent to, the molar mass is 159.7 grams per mole, if you recall. Then the number of moles that will be found according to this is 48.5 divided by 159.7. This is going to give us a 0.304 moles. So if we convert it to moles, then just compare how many moles of carbon monoxide are needed to react. So we are going to go direct. So according to this, 3 moles is able to react with 3 moles is able to react with, so remember it's now iron 3 oxide, so the reactants. So 1 mole of iron 3 oxide is able to react with 3 of them. So we are going to say 1 mole of iron 3 oxide is able to react with our 3 moles of carbon monoxide. Carbon monoxide. How about if you have 0.304 moles of carbon monoxide? Here you don't know, so you're going to cross multiply, which will give you a 3. So cancel that. We have 3 times x, it will be 3x. 1 times this, it will just be 0.304, like that. Moles of our Fe 2 or 3 like that. We divide by 3, which will give us a value of our 0.304 divided by our 3. This is going to give us a value of x should be equal to 0.101 moles of our Fe2O3. Oh, there's a slight mistake. This 0.304 was the moles of iron 3 oxide. So we are supposed to put it where iron 3 oxide is. So we are supposed to put it where iron 3 oxide is. So our iron 3 oxide is here. So we have our 0.304 moles of our iron 3 oxide should be equal to x. So we cross multiply. This and this cancels to give us 3 times this. So x times 1, it will be x should be equal to 0.304 times the 3 of carbon monoxide, 3 moles of carbon monoxide. So when we multiply, we are getting a 0.304 times our 3. This is going to give us a value of a 0.912 moles like that as the required answer of carbon monoxide. This one says, how many grams of iron are formed when 18.6 grams of carbon monoxide react? So we have how many grams of iron are formed when 18.6 grams of carbon monoxide react. So we are going to have our carbon monoxide. Let's convert it. So carbon monoxide, the molar mass will be, we have 16. The mass of carbon, molar mass of carbon is 12.01. When we add, we are going to get a, so when we add, we are going to get a 28.01 like that grams per mole. Then we are just going to say the number of moles is equal to the mass over molar mass. So if we have been provided with a mass which is 18.6 grams, so we have 18.6 grams over the molar mass, which is our 28.01 grams per mole, which is going to give us a 18.6 divided by 28.01 like that. So when we do that, we are going to get a 0.664 moles like that. So these are the number of moles. Then all we have to do is that we are going now to answer the question, which is how many grams of iron are formed when this number of grams react. Mass to mass can also work, but for many of you, you are not conversant with that method, so let's just go with a simple one. So upon conversion, we are going to have, these are the number of moles of carbon monoxide. What do we want? We want how many grams of iron are formed. So we are going to be comparing carbon monoxide and iron. So we are going to say 3 moles of our iron, according to the equation, should be able to give us 2 moles of our iron like that. What if we have the 0.664 moles of our carbon monoxide? This is going to give us x like that. Then we are going to cross multiply. We have our this one goes, so we have our 3 times x, it will be 3x should be equal to 0.664 times, it is multiplying with 2. We divide 3, we are going to get a value of, so if we divide our 3, so 0.664 times 2 divided by our 3, we are going to get x should be equal to 0.443 moles like that. But we want the this is 4, or should I say of iron. Yeah, so remember we cancelled this, we remained with the moles of our ion like that. So if they are on the same side, cancel them like that. So now then the mass, remember we said mass is equal to the number of moles times the molar mass. So the number of moles is equal to, we have a 0.443 moles times the molar mass, which is equivalent to 55.85, that is for iron, grams per mole. So when we multiply this, we are going to get this value times 55.85. This is going to give us a 24.723 grams like that. Not the molar mass, but the mass like that. So that is how we deal with that question. So this other equation says, question 3, reactions in aqueous solution. Then we are told define the following terms and define the following terms and each an example of each. Give an example of each. So we have the weak electrolytes. So a weak electrolyte is one that partially dissociates in water. So a weak electrolyte is a substance that partially dissociates in water. So the example that we might have is ethanoic acid. So ethanoic acid is a weak acid because it does not fully dissociate, or rather ionize. If you don't want to use dissociate, you can use ionize in water. Then for Arrhenius acid, so Arrhenius acid so by definition, an Arrhenius acid, so remember, an acid is a substance which dissociates in water to produce, or rather ionizes in water to produce hydrogen. Now here for Arrhenius acid, it's a bit tend a bit. So we know to say hydrogen, yes, is produced, but hydrogen in water will exist as an ion, which we call hydronium ion. So we are going to define Arrhenius acid as a substance that increases the concentration of hydronium ions. So that is what we call an hydronium ion. That means to say, an Arrhenius acid. That means to say an Arrhenius base is a substance that increases the concentration of hydroxide ions in a solution. So in case you are asked the other one, let's move on. We have this question. It says a 1 liter sample of contaminated Kafua River water was analyzed for lead 2 ions, that is Pb2 plus, by adding an excess of sodium sulfate to it. The mass of lead 2 sulfate that precipitated was 229.8 milligrams. Write a balanced chemical equation for the reaction above. Number 2, write the net ionic equation for the reaction in B1. Calculate the mass in milligrams of lead in water. So the first thing, so we have a sample of contaminated, a 1 liter sample of contaminated Kafua River water was analyzed for lead 2 ions by adding an excess of sodium sulfate to it. The mass of lead 2 sulfate that precipitated was this. Write a balanced chemical equation for the reaction. So now here you need to be very, very careful. So we have lead ion. It exists as an ion. You don't write lead hydroxide because it's water, it will combine with water. If they are telling you lead ion, it simply tells you to say lead ion can be formed by a number of things. It could be lead nitrate, like that. It could be a lot of things. So therefore we do not know what this ion is combined with, so we cannot necessarily say we combine it with an hydroxide or anything. So we're just going to say it's an ion. We add AQ plus the balanced chemical equation plus we have the excess of this was added sodium. So we have sodium sulfate, which is Na2SO4, which is in AQ. To produce, what we are going to have is that we are going to produce Pb, like that, lead. Then this lead will be able to displace the sodium, so it will be lead sulfate, like that. Remember, lead has got a valency of 2. Then we have plus the nitrogen, the sodium, like that. So this will be the precipitate that is formed like that. So this can even be in AQ state or even solid. The state symbols here are not important, but for this one, since it's a precipitate, you have to add the solid there. So remember one cardinal thing. If we have this situation, we have this one. Since it's positive there, it's an ion, meaning to say there was something it was bonded to. So whatever it was bonded to, that is what the sodium will take. So sodium will exist as an ion to combine with whatever lead, the unknown thing that lead was bonded to. So with that, we are going to say the state symbol will be AQ, since our sodium is in AQ state, or rather it's an ion. And remember, precipitation involves reacting two soluble salts to produce an insoluble salt and a soluble salt. So balancing this equation, we are going to just put a 2 here. Where else? So we are going to put a 2 here. Just a 2 will be enough. Then, if that is what we have, so this is the equation they wanted, 3 marks. We are going to go to our second part. We have write a net ionic equation for the reaction in B1. So for the reaction in B1, we are going to have something like this. So B1, this was our 3 marks. Then for this one, to write the net ionic equation, meaning we cancel the spectator ions, so we are going to have our Pb plus, we have our AQ plus, this one dissociate it, so this 2 goes in front of sodium, so we are going to have 2 sodium plus, which is in AQ, plus our SO4. The valence of sulfate is negative, like that, -2. Then this will be able to produce our Pb SO4, like that, a solid. Then we have plus our 2 moles of sodium ion, which is our AQ as well. So with that done, we have done that. Then we just cancel whatever is common. So as you can see, what is common here is this one with the same state symbol. So this one is common with the same state symbol. So we are going to cancel that. So this and this goes. Then we are going to remain with our Pb, 2 positive, our AQ. Then we have plus our SO4, 2 negative, AQ. This should be able to give us our Pb, SO4. Then we have the solid, like that. We get our 3 marks. Let's move on. For this one, we are told calculate the mass in milligrams of lead in the liter of water. So if we have our Pb, 2 positive, plus our SO4, 2 negative, AQ to produce the precipitate, which is our PbSO4. Now, which is a solid. What is the mass in milligrams of lead in the liter of water? So we want the mass of lead. Now, what are we going to do? So what we are going to do is, remember, so if we have this substance, just use the concept that we used. So the amount or the mass of lead in the liter of water, we know that all the lead that is here is the one that has caused there to be the lead. there. So we are going to use this approach. So we can say to find the mass of lead, we are going to use the same concepts of, I think you can think of it as percentages, which we are going to have our mass of Pb, our molar mass of Pb over the molar mass of the compound, which is, in this case, it is existing like this at the end, because that is what we have, because this is the mass that was precipitated. The precipitated mass was this, meaning to say that is the final mass of this. So the molar mass of our Pb, SO4, then we multiply by the total mass of our Pb, SO4. So this is going to give us, so if you look on your periodic table, the molar mass of our lead is equivalent to, should be 207.2, but let's find the molar mass of PbSO4. So we have our PbSO4. So we have 4 times, there are 16, or there are 4 oxygens times 16. Then we have our sulfur is 32, like that. Then we have our lead is 207.2, like that. So when we do that, we have our 4 times our 16. This is going to give us a 64. Then we have our 32. We have our 207.2. When we add them, we have plus 207.2 plus our 64. We are going to get a value that is equivalent to. So when we add these, we are going to get a 303.2 grams per mole. So if we know that now, we can just replace. So the molar mass of Pb over the molar mass of our Pb SO4, then we have times our, not 100%, but times the total mass of the Pb SO4, which is the actual. So we have 207 is the molar mass for Pb, grams per mole, over the molar mass of PbSO4 is equivalent to, we have found it to be 303.2 grams per mole. Then we multiply this by the total mass, which is a 303.2 grams, like that. No, not 3 point. What was the actual mass? It's more like we're finding a percentage. So the actual mass was 229 point, is it a 3? 229.8 grams, like that. So we have our 207 divided by 207.2 divided by 303.2. Then we multiply this by 229.8. 157.04 grams should be equal to the mass of our lead present, because it's a percentage. So looking at this other one, use the half reaction method to balance the reaction below in acidic media. So if we have our Zn plus our Br or 3 negative to produce our Zn 2 positive plus our Br negative, like that. So we are required to write the half reaction to balance in acidic media. Remember, an acid produces a hydrogen ion, so we are going to add hydrogen because we can play around with hydrogen. It is ever present, and we can add water when balancing in acidic media. So let's write the half reaction. So the half reaction for the first part, which is our Zn. So Zn can be able to become Zn2 positive, like that, provided that we have, so this type of a reaction, so we have an increase of oxidation state from 0 to 2. So this one we are going to call it oxidation, like that. So we have oxidation is the increase in the charge, like that. So what we are going to do is that since we have our Zn, we have 2 of them, or we have the charge of positive 2, so we need to have 0 this side and 0 that side. So meaning to say we are going to add electrons 2 electrons plus the positive 2 will give you a 0 like that. So we have this reaction will be just like this. So we have balanced that one. So if that is oxidation, this has to be reduction. So the full video on balancing in acidic oxidation and reduction has already been uploaded. So we are going to have the other part, which is our BrO3 negative. It is O3 negative, should be able to become our Br negative, provided that, so this one is reduction. As you can see, oxygen has also been removed. So if here there is oxygen, more oxygen than this side, we are going to add water, because water is ever present, they are occurring in water. So we add water that side, then from there balance the number of water molecules. So if you have 3 oxygens this side, you are going to add 3 so that the oxygens can balance in that way. Then from there, this side, since you have introduced hydrogens, there are 6 of them, 3 by 2 is 6, so you are going to add hydrogen ions which are ever present. How many? 6, because 3 times 2 is 6. So we are going to have, let me reduce the equation a bit. So now if we look at the charge, we have a negative here, we have a negative here, here we have a positive 6. So we are required to have the same charge, but as you can see, this is negative 1 and this one is negative 1. So to eliminate this excess charge, just add other electrons such as 6 electrons, so that these and this will be able to cancel and remain with that. So with that done, we are going to go on to our next step. So if that's what we have, we are going to now be able to just interchange. Let's get these 2 equations. So here there is a 2, so we are going to interchange the number of electrons. Here there is a 6, so we are just going to interchange them. So here we are going to have our 2 number of electrons. Here we are going to have our 6, so just interchange 2 and 6 number of electrons, just interchange them like that. So 6 times Zn, it will give you 6 Zn to produce this 6 times Zn there, it will be 6 Zn 2 positive, 6 times 2, that will give us a 12. So we have 12 electrons. Then we have our 6 times 2, it will give us our 12 electrons. 6 times 2 here, it will still give us 12 hydrogens. Then we have plus this, we are going to have 2 BrO3 negative to give us 2 times Br, it will be 2 Br like that. Then we have negative plus our 2 times 3, it will give us 6 H2O like that. So this is what we have for that problem. Then what we are going to do is that, as you can see, the number of electrons here and here are the same, so we are going to cancel them. So this and this cancels, we are going to remain with our 6 Zn. Then we just add plus, we have our 12H plus ions plus our 2 BrO3 negative to produce our 6 Zn 2 positive. Then we have plus our 2 Br negative plus our 6 H2O like that. So this is our answer for that problem. Is there anything common? So something that is common here is a 2 can enter into all these numbers, so we are going to divide 2 throughout, so that we have the final equation. It will be 3 Zn plus 6 H plus our BrO3 negative to produce our 6 divided by 2 will give us 3 Zn 2 positive plus our Br negative. Then we have plus our 3 H2O like that. So this is what we have as our final answer for that problem. We obtain our full marks like that. So the last part is gases. So the last part we are on gases. So a sample of nitrogen gas occupies this at 100 degrees Celsius at the temperature in degrees Celsius. At what temperature in degrees Celsius would it occupy 234 if the pressure does not change? So if the pressure does not change, we are looking at Charles' law. So let's answer the question. Let's just move this question a bit. So moving this question. So here what we have is Charles' law. According to Charles' law, the volume is directly proportional to the temperature. Therefore, the formula for Charles' law, if you take the T here, you're going to have the V, or should I say, if you introduce now the equal sign, you have your V is equal to T. So KT over T over T. So that's why our Charles' law, we have the Charles' law is equal to volume number 1 over the temperature number 1 should be equal to volume number 2 over the temperature number 2. So the volume number 1 in this case is equivalent to this. So we are told at what temperature in degrees Celsius would it occupy 234. So if the volumes are in the same units, you can use them like that. It will give you the same correct answer. So now what we are going to have is that let's convert this temperature to Kelvin. So the temperature, according to Charles' law, it always has to be in the absolute temperature, which is in kelvins. So the temperature in kelvins should be equal to temperature in degrees Celsius plus 273.15 degrees, 0.15 degrees. This is going to give us a value that is equivalent to, we have the temperature in degrees Celsius is equivalent to, we have 100 degrees Celsius plus 273.15. So we can have 1 Kelvin on top over 1 degrees Kelvin. If you want, you can just add direct without this if your lecturer is not strict. So we put the C here so that the C's can cancel there. So we have our 100 plus 273.15. This is going to give us a value of 373. So we have 373.15 degrees kelvins, like that. So with that said, we can now replace. So we know to say, let's move this a bit. So knowing to say, according to Charles' law, we have the volume number 1 over the temperature number 1 should be equal to volume number 2 over temperature number 2. So the volume number 1 is equivalent to, we have 117 milliliter over the temperature number 1 is equivalent to, we converted this to 373.15 kelvins should be equal to temperature number 2 or volume number 2 is, according to what we are given, it's 234. So we are going to write our 234 like that, 234 milliliter over our unknown temperature number 2 like that. All you have to do is cross multiply there so that this becomes equal to, we are going to have something like T2 times that, it will be 117 milliliter times our T2 should be equal to 373.15 kelvins. Then we have times our 234 milliliter like that over our 117 milliliter over our 117 milliliter like that. So our temperature number 2 will be equivalent to, if we press everything, we have 3 times 234. Then we divide this value divided by our 117. This is going to give us a temperature of 746.5. Remember, it will give you 0.3 kelvins. So the temperature will give you in kelvins, but they want what temperature in degrees Celsius. So temperature in degrees Celsius. So this temperature in degrees Celsius, we know to say it's temperature in kelvins. Remember, you're moving from K to that, you have to subtract because of the alphabet. You can think of it like that. So we are going to subtract. By subtracting, we are going to have temperature in degrees Kelvin, which is our 476.3 degrees Kelvins minus our 273.15 degrees Kelvins. We can have the 1 degrees Celsius over 1 degrees Kelvin, like that. So we are going to have minus our 273.15. This is going to give us a value of 473.15 degrees Celsius. So this is the temperature required for that. Let's move on to our next question. B says, what is the volume occupied by this amount at the temperature of -25 and 752 milliliters of mercury? So to answer this question, if they have given you the volume, the temperature, and the pressure, just think of the ideal gas law. So we know that it's PV should be equal to nRT. So dividing P to make the volume the subject of the formula, we are going to end up with V is equal to nRT over the pressure, like that. So our volume should be equal to, now the pressure, we are going to be using our R is equal to 0.08206. So our pressure has to be in ATM. So converting the pressure to ATM, we are going to get the value. So let's convert the pressure, convert the temperature, has to be in kelvins. So gases mostly is about converting. So let's begin with our temperature. So the temperature in degrees should be equal to temperature in kelvins plus 273.15. So let's just convert direct. So we are going to have our temperature in degrees Celsius, which is equal to, we have -25 degrees Celsius plus our 273.15, which is going to give us a -25 plus 273.15. This is going to give us a value of 248.15, like that. So this is the temperature in degrees kelvins, like that. So this is the temperature in kelvins. Then convert as well the temperature, the pressure to atmospheres. So if you have your 752 millimeters of Hg, so remember what you are going to do is you are going to put on top, you are going to put the one that you want to convert, which is the atmosphere. Down here, since there are millimeters of Hg, you are going to put them there. Then put the values. In 1 atmosphere, there is exactly 760, like that. So this and this cancels. So when you divide your 752 over your 760 times 1 ATM, you are going to get a value that is equivalent to, we have 752 divided by our 760. This is going to give us a value of 0.989 ATM. So with that said, we are going to say the volume, which is equal to nRT over the pressure. We are going to replace V is equal to, what is the number of moles? Wow, there was a lot of conversions here. So 20.2, we have to convert that to, so we have the number of moles is equal to the mass over the molar mass. So our mass is equal to 20.2 over the molar mass, which is NH3. We are going to have hydrogen, it's 1.01 times our 3. Then we have our 14.01. So if we add 3 times this value, it will be equal to 3.03 plus our 14.01. When we add these, we are going to get our 3.03 plus our 14.01. This is going to be able to give us a 17.04 grams per mole. like that. So if that's the case, we are going to put it here 17.04 grams per mole. Then here on top we are going to have our grams like that. The number of moles will be equal to, we have our 20.2 divided by 17.04. When we do that, we are going to get a 1.1854 moles. So with this number of moles, we are going now to just replace, we are going to replace the volume is equal to nRT over our pressure. So the number of moles is 1.1885 moles times the gas constant, which is our 0.08206, times what is our temperature. So our temperature is equivalent to, what do we have, 248.15, if I'm not mistaken, 0.15 kelvins. So 0.15 degrees kelvins. Then we divide this over our other value, which is equivalent to the pressure. We found the pressure to be equal to 0.9, where is it, 0.989 atm, like that. So when we do that, the final answer, when we press everything, times 0.08206 times 248.15, then this value divided by 0.989, this is going to give us a 24.41. So this is the volume, which is in liter. So for this one, we have we have a 250 milliliter vessel, contains 1.02 grams sample of a gaseous compound and 25 degrees Celsius and 750 millimeters of mercury. What is the molar mass of the compound? So provided the mass, they want the molar mass. So what we are just going to do is, we are going to use the one that has already been made the subject of a formula. So just spell the word doctor with big letters. Doctor as a T should be equal to Mr. P, like that. So this is the formula we are going to use to find the molar mass, which is this one. So you can just change it to the molar mass like that. So now, so this will be over our pressure, so that will be our molar mass. So the molar mass is equal to density, like that, over the pressure, like that. So now let's just find the things. So density, we know that it's mass over our volume. So mass over volume is density. So density will be equal to our mass, according to what we have been given, is a 1.02 gram. So we are going to say 1.002 grams over the volume. The volume is equivalent to, we have a volume of 250 milliliters. So 250, then where there is the milli, you can put 250, not 550. We have 250. Milli is a unit of 10 to the power negative 3 liters, like that. Then we are going to calculate. So our density will be a 1.02 divided by a 250 times our 10 to the power of negative 3. So we are going to have something like the value, which is equal to a 4.08 grams per liter. So we have found our density. Then all we have to do is, let's convert the temperature to degrees to kelvins. So the temperature is given as 25 degrees Celsius. So let's convert it. So we have the temperature in Kelvin should be equal to temperature in degrees Celsius plus 273 point. We have 15 like that. So we are going to have 25 degrees Celsius plus 273.15. The temperature will be equivalent to, we are going to have our 25 plus 273.15. This is going to give us a 98.15 like that. So this is the temperature in kelvins, so we can put the temperature in kelvins like that. Pressure we convert from the unit of from millimeters of Hg to atmosphere. So we have 750 millimeters of Hg. We multiply this by, we have since there is the millimeters of Hg down here, so that they can cancel. Up here we are going to have atmosphere. 1 atmosphere, there is 760 like that. This and this cancels. We are going to have our 750 divided by our 760. This is going to give us our 0.9868 atm. This will be our pressure in atm. So the pressure is 0.9868 atm. We have the temperature in kelvins is equal to 298.15. Then we also have the density is equal to 4.08 grams per liter. So we can, using our doctor, T should be equal to the Mr. P, like that. So we made it the subject of a formula. We have over P, so molar mass. So the molar mass should be equal to the density. We found it to be 4.08 grams per liter times R is equal to, our R is 0.08206. Then we have times, what is our temperature? Our temperature is equivalent to, we have the temperature is equivalent to 298.15 like that kelvins. Then we have over the pressure, which we found to be 0.9868 atm. So our molar mass, if we press everything, we are going to have 4.08 times 0.08206 times 298.15. Then we divide this value divided by our 0.9868. This is going to give us a 101.16 grams per mole. So that is what we have found. Looking at the next question we have, so answering this one, we have what is the pressure in atmospheres exerted by the mixture of 1 gram of hydrogen and 5 grams of helium when the mixture is confined in a volume at this temperature? What are the partial pressures and the of hydrogen and helium? Calculate the mole fraction and the mole fraction of hydrogen and helium gases. So 10 marks. So what we are going to do is that from here we are going to begin with the partial pressures. Use the partial pressures to add the pressure of the mixture. That means to say we have answered 2 parts, then answer this separate. So there are 2 ways of answering the first one, but let's just use Dalton's law of partial pressure. So before we do that, the first thing that you need to do is convert each and everything to the required units. So if you have the H2, so you have the mass of 1.0 grams, I can just say 1 gram of my H2. I need to convert this to the moles. Then I also have my 5 grams. I need to convert this to helium. I need to convert this to the required units. So for hydrogen, we have hydrogen gas. The molar mass will be 2 times 1.01, so it will be a 2.02. So we are going to have the number of moles is equal to the mass over the molar mass. So the number of moles is equal to what is our mass? Our physical mass in this case is equal to, we have 1 gram over the molar mass of hydrogen, which we have found to be 2.02 grams per mole. So if we divide this, we are going to have our 1 divided by 2.02. This is going to give us a 0.495 moles. So if we find the number of moles, we are going to find also the number of moles for this. It's 5 grams divided by, we have our 4 grams per mole. So the number of moles in this case will be equal to 1.25 moles of helium, like that. From here, we can just go direct to find the first part, which is calculate the pressure of the exerted on that when the mixture is confined. So what is the pressure exerted by the mixture, meaning the two? So to find the pressure by the mixture, so we can say pressure by mixture, we can add the two pressures. It's either we can solve them separately or we can do this. Pressure by the mixture will be the number of moles, which is the total number of moles will be equal to 0.495 moles, like that. We add plus the 0. We have 1. We want the total number of moles because it's a mixture, 1.25 moles, which is going to give us this plus 1.25, which is going to give us a 1.745 moles. So this is the total number of moles. Therefore, if this is the total number of moles, we are going now to replace. So we have our N total, like that. Therefore, the number of moles is equal to the mass over the molar mass. Oh, we have found the number of moles using the pressure, using the law, which is the ideal gas law, if we have been provided volume and all that. So using this, you can now calculate the total pressure using the total number of moles. Now, provided that the temperature is in degrees Celsius converted, so the temperature in kelvins should be equal to the temperature in degrees, which is 20 degrees, plus the 273.15. This is going to give us a 20 plus 273.15. This is going to give us something like a 293.15, like that. So this is the temperature in kelvins. Then just replace. So the total pressure will be equal to nRT, like that. So our number of moles is, the combined is 1.7. Where is it? We have 1.745 moles, 45 moles, times, what is my R? My R is equal to 0.08206. Let me move this. So we have times our temperature. So nRT, it is PV. So it's PV is equal to nRT. So we have to divide over V to make P the subject of a formula. Then the temperature, we have found it to be 293.15. We divide this by the volume, which is equivalent to, what's our volume? Our volume is equivalent to 5 liters. So we are going to divide the 5 liters like that. Then we are going to get a 1.745 times our 0.8206 times our 293.15. we are going to have a 419.775. We divide this over our 5. We are going to get a, sorry for that, the decimal point supposed to be here. Correct multiplication is cardinal. We divide by 5. This is going to give us 8.395, or should I say 6 atm. So this is the total pressure. So this is the total pressure of the mixture, like that. Then for the partial pressures, we are going to do the same. we are going to do the same. We have the partial pressure. According to Dalton's, it is the pressure of a gas in a container as if it is alone. So that's the partial pressure. So to begin with, let's begin with our hydrogen, which was the first thing mentioned. So the partial pressure of hydrogen will be equal to, not helium, of hydrogen will be equal to the number of moles of hydrogen. Then we have our RT like that, divided by the volume. Just the normal PV is equal to nRT, making V the subject of a formula, we divide by V like that. So nRT over our V. So this is the pressure of hydrogen. So the pressure of hydrogen will be equal to, what are the number of moles of hydrogen? So if you recall, the number of moles of hydrogen was found to be equal to 0.495. So we are going to say 0.495 moles. We multiply these moles by the R, which is 0.08206. Then we have times our temperature, which was found to be 293.15. We divide this over its volume. So the volume is equivalent to, as if it is the only gas. So you consider the whole volume, which was a 5 liters like that. So the pressure of hydrogen gas is equal to, we are going to multiply, so 0.4495 times 0.08206 times, we have our 293.15. Then this value we divide it by 5, we are going to get a 2.382. So this will be our pressure in atmospheres. Likewise, our pressure, our partial pressure, so we are partial pressure of helium will be equal to the number of moles of helium, RT over the volume like that. So as if it is alone, that is Dalton's law of partial pressure. So we have the number of moles in this case is equivalent to, we found the number of moles of helium, if you recall, it was a 1.25, which is this one. So we are going to put the 1.25 there. We are going to put a 1.25 there. So 1.25. Then we have times our R, which is 0.08206. Then we have times our temperature, which is equal to 293.15 kelvins, divided by the volume, which is our 5 liters. So we are going to have a 1.25 times 0.08206. Then we have times 293.15. This is going to give us a value divided by 5. This is going to give us 6.014 atmospheres. So this is the partial pressure. Remember, as if it is alone. You will find that if you add this and this, you are still going to get the total pressure. So if you were required to find the total pressure, you can also use this. You find the partial pressure of each, then add the two pressures. It is still going to give you the same 8 point something that we found. Then the last part of the question says, calculate the mole fraction of the gas. Calculate the mole fraction of the gas. So for mole fraction, we are going to say mole fraction. So the mole fraction of the gas, it will be equal to, it is a fraction, so therefore the mole fraction with the symbol X, it will be the mole fraction of let's say hydrogen, it will be equal to the number of moles of hydrogen over the total number of moles. So the number of moles of hydrogen was, if you recall, the number of moles of hydrogen was 0.495 moles over the total moles, which is our, when we added the moles, we had a 1.746. Then when we divide, we are going to get a 0.495 divided by a 1.746. This is going to give us a value that is equivalent to what do we have? 0.284 rounded off to 3 significant figures. So this is our mole fractions, our mole fraction of hydrogen. Likewise, the mole fraction of helium will be equal to the number of moles of helium over the total number of moles. So the number of moles of helium was found to be 1.25. We divide it by the total, which we found to be 1.746. So we have the moles. Remember, it does not have units. So we are going to have our 1.25 divided by 1.746. This is going to give us a 0.17 like that. So it's a fraction. That is what it's going to give us. Is there? Yes, we have done that question. So for E, it says that calculates the pressure exerted by 1 mole of ammonia in this amount of a vessel, assuming non-ideal behavior. So we are going to have our P plus our A, then we have our N over V, then we have squared. So this is the formula for the ideal gas equation. Then we have times our V minus our NB should be equal to nRT. So this is the equation. So we are going to now just divide. We want to make pressure the subject of the formula. So divide over N, divide this. You can even extend it to that. Then here we have N minus V minus NB. So this and this cancels. We are going to remain with our P plus our A. Then we have our N over V. Then we have squared should be equal to, we have our nRT over our V minus our NB like that. We take this value this side, it will be pressure should be equal to our nRT over V minus NB. Then we have minus our A, N over V. Then we have squared like that. So let's solve. We have calculated the pressure exerted by 1 mole of this in a 500 milliliter vessel at this temperature, assuming no ideal behavior, meaning we are looking at the real gas equation. So this is the equation, taking that. So this is the equation we are going to use. So our pressure, first let's convert the temperature. Temperature will be equal to, what do we have? We have we add temperature in degrees Celsius plus that temperature in degrees Celsius plus 273.15. So we have 25 degrees Celsius plus our 273.15. So when we add that, we are going to get so 273 plus 25. This is going to give us, so we have 25 plus 273.15. So this is going to give us a 298.15 like that. So this is the temperature in degrees Kelvins. So therefore, after we do that, we are going to substitute. We have the pressure will be equal to, we have 1 mole like that, times our R is equal to 8 point, our R is equal to, we have times 0.08206 times the temperature is 298.15. Then we divide over our 2, over our V minus NB, and we know that the what's this, the volume is 500 milliliters. So we can put 500 milli is 10 times to the power negative 3 liters minus what's our number of moles. So our number of moles is equal to, we have 1 times our B. So we have our NB. Our B is equal to 0.0371, 0.0371, like that. Then we subtract this minus our A, which is this part, A over N minus that. So let me reduce the font. So we have our minus, our A is we have a 4.17, so we can replace it there, 4.17, like that. We multiply by the number of moles, it's 1 mole, over, so we have our N over V. So we are going to write our V is 500 times 10 to the power negative 3 liters, like that. Then we square this. So we are going to have the pressure of, we have our 1 times 0.08206 times 298.15. Then we divide, we are going to have on top, we are going to have 24.47. We divided by 500 times 10 to the power of negative 3. This is going to give us a 0.5 minus 0.0371. Then we have minus, we have a 4.17 times 1 divided by our 500 times 10 to the power negative 3. That is going to give us a 2. So we get a 2 there, we square it. Final answer, pressure should be equal to 24.47 divided by our 0.5 minus 0.0371. This is going to give us a 52.86 minus, we have 4 times 4.17. This is going to give us a 16.68, like that. So this is going to give us, if we subtract our 52.86 minus our 16.68, this is going to give us a 36.18 atmospheres. So that is how we answer that. Thank you very much for watching. Hope you would like, subscribe and share for more. See you in the next tutorial.